Welcome back to ECE 442-542. This is lecture 6.2, the first part of that, part B, and in this particular section of lecture 6.2 we'll be talking about the root locus conditions, and then we'll give you a quiz. So let's now look at this block diagram. Here's our traditional, or this is now the standard form that we will be using when we're drawing root locus diagrams. And notice that I've actually introduced a bar on the G, so this is now G bar. This is not necessarily the standard plant that we're used to seeing. This is now a modified or a generalized plant. And by a generalized plant, what I'm meaning is it's the original plant, G, and it's the poles and zeros that might be part of the controller. And what we've done is we've explicitly factored out of that controller the gain K. So we now have two pieces that could be creating this G bar, but for now just think G bar is some collection of zero factors and pole factors, and the gain has been slid out or explicitly isolated in this one block that we're labeling K. So this is now the root locus diagram. This is the standard configuration. It's unity output feedback, and with this configuration we can find the closed loop transfer function between the reference input R and the output Y, and that's just K G bar over 1 plus K G bar. It's this forward gain K G bar over 1 plus the forward gain K G bar. The closed loop dynamics are determined by the denominator of T of Z of that closed loop transfer function, and the closed loop dynamics are then governed by 1 plus K G bar of Z, and the dynamics are those modes, those values of Z that cause 1 plus K G bar to equal 0. That expression right there, that in fact is what leads to the root locus conditions. And the rules that we will use to sketch root locus diagrams all hinge on or arise from these conditions. The root locus conditions, if we now subtract 1 from both sides of this equation, we get rid of that 1 and we're left with Kg bar, and on the right we have minus 1, but since G bar in general can be a complex number, let's rewrite minus 1 as a phasor or as a complex number. This is now 1 at 180 degrees, or more traditionally I'm going to just make it minus 180 degrees. That 180 degrees is the same point. So now minus 1 is over here, and we can get there either by going through 180 degrees up, or we can get through or get to that point minus 1. We're a distance 1 from the origin in the complex Z-plane, and we can get there either by going through a positive 180 degrees or a negative 180 degrees. I'm going to traditionally go in the negative direction so that we have a negative lag in our understanding, or a negative angle more commonly in our expressions. The root locus conditions then all hinge on kg bar equaling -1 or kg bar equaling 1 at an angle of -180. This left-hand side is a complex number. The right-hand side has a magnitude and a phase. The phase angle condition, and we'll just restrict our treatment of the root locus in this class to always correspond to k being non-negative. If k is non-negative, that doesn't influence the angle of kg bar. Kg bar then, its angle is determined all by the angle of g bar. This equation now has two conditions. It has a phase condition and a magnitude condition. The phase condition says that the angle of the left-hand side equals -180 degrees. That's true for those values of z that satisfy this equation. Also, we know that the magnitude of this must have a magnitude of 1. So we have two conditions, and these two conditions all, or basically now, determine the rules that we will use to sketch root locus diagrams. Now, we're interested in finding angles of poles and zero factors. Let's now take a quiz. Let's see if you know how to do that. Suppose I now ask you, what is the angle of g bar of z at this location in the complex plane, z equal to 1/2 plus j 1/2, when g bar is a particular collection of zero factors and pole factors? Initially, let's just assume that it's two poles. One pole is at the origin and one pole is at z equal to 1. Those are the values of z that cause that denominator to vanish. We can sketch this, and that's actually how we can now determine this angle at that point in question. The point in question I'm now showing as that triangle. That triangle now is the location of z in the complex plane at 1/2 plus j 1/2. We go to that spot and we say, if I'm now standing at z equal to 1, what angle do I now need to turn through? If I initially begin my stance pointing in the positive real direction, I now want to rotate my body. I want to rotate. That pole was originally looking towards positive infinity. Now I want to rotate. What angle do I move through in order to see that triangle? Likewise, if I'm at the origin, that origin pole will also produce an angle that I'm labeling theta sub p sub 0. And notice that theta p sub 0, I don't have to turn as far to see that triangle as I need to turn through theta p sub 1 in order to see that triangle. And you could actually pull out a protractor and measure those, or we will numerically calculate those. But for now, we don't have any zeros present in this transfer function. We don't have any finite zeros. Consequently, the angle of this real number, 1, is 0 degrees. So if I now say 0 degrees there, that's where that 0 degrees is coming from, the numerator's angle. I then subtract the angles due to the denominator terms in order to find the complete angle of g bar. So I have the angles from the 0 upstairs, and those now are used to produce this collection of angles, which in this case is just one angle of 0 degrees, and I subtract the angle of that factor and the angle of that factor. The angle of the pole at the origin I'm calling theta p sub 0, and the angle at the pole at z equal to 1 I'm calling theta p sub 1. And we can actually just eyeball those. I hope you can see that in fact the angle theta p sub 0, we go over 1/2 and up 1/2. This particular angle is 45 degrees. Similarly, we could say, okay, if I can actually measure this angle, that angle is going to be over 1/2 and up 1/2, and so theta p sub 1 is in fact 180 degrees minus that acute angle of 45 degrees, or that's 135 degrees. Which really says that we're subtracting from 0 45 plus 135, or the angle of G bar, this was your quiz answer, is minus 180 degrees. We could have calculated that from the transfer function itself, which is really just evaluating G bar when we replace Z with that triangle location. Remember this 1/2 plus J 1/2 was the triangle spot. We now use that number. It's a complex number. We replace Z everywhere with that number. And that's what I've done here. Here is 1/2 plus J 1/2 times 1/2 plus J 1/2 Z minus 1. I didn't do anything to the first term, but now in the next iteration of that expression, I simply said 1/2 minus 1 is minus 1/2. So my second factor in the denominator is minus 1/2 plus J 1/2. I can factor out a 1/2 so that maybe my complex number is easier to think about. I have a complex number of 1 plus J1, and here I have a complex number of minus 1 plus J1. And the magnitude I've now factored out to be 1/2 and 1/2. And now you should be able to find the magnitude and angle of that complex number. It's the square root of 1 squared plus 1 squared. That's the square root of 2. And the angle, it's over 1 up 1. That's 45 degrees. This is now the complex representation of 1/2 plus J 1/2 in rectangular form in polar form. Likewise, I can convert this to its polar form. I already have the 1/2 scaling part of the magnitude. I have real part squared plus imaginary part squared. That's exactly the same length that I had before, square root of 2. Now I go back in the real line, minus 1, and I go up 1. That's an angle of 135 degrees, as we know here for theta P1. I combine those angles by adding them. These are just phasors, and so I can now multiply the magnitudes together. That's 1/4 times 2. I can add the angles. I now have, if I look at this, what do I have? I have 1 divided by 1/2 at an angle of minus 1, at an angle of 180 degrees. But if I now take this number upstairs, that 1/2 becomes 2, and I subtract that 180 degrees from 0 to obtain minus 180 degrees. That's now saying that as a complex number, I'm away from the origin, a magnitude of 2, and I'm at an angle of minus 180 degrees. That's where I'm standing in this complex z-plane, is at 2 at an angle of minus 180, and if I just want to extract the angle from that complex number, I say, oh, my angle is minus 180 degrees, and in fact, this particular collection of poles and zeros, 1 over z times z minus 1, verifies that that point would lie on the root locus because it has an angle of minus 180 degrees. And that's what all points that live on the root locus have to have. They have to have angles of minus 180 degrees. What if we modified that g bar and now made it have a zero factor, z plus z sub 0? And for kicks, now let's just locate that z sub 0 at some location. Maybe we let z sub 0 equal 1, so that we now are at a point minus 1 in the complex z-plane for our 0 location. I now do have an angle, theta sub z, associated with that. What angle do I have to look through in order to get to that triangle, or to be lined up with that triangle? And this is about 20 degrees, it looks like. The theta p0 and the theta p1 have not changed. This is still 45 degrees. This is still the 180 minus 45, or this is now the 135 degrees. This is approximately 20 degrees. I now have 20 minus 180, or this is now minus 160 degrees, roughly. And that means that that point now no longer would lie on the root locus. We can again calculate that. We still have this z plus 1 as a factor. With z sub 0 here, I'm setting z sub 0 equal to 1 in this expression. Now I have, again, I have 1/2 plus j 1/2 plus 1. Or I now have 3/2 plus j 1/2. Or I can take the 1/2 out and I have 3 plus j. I'll go ahead and just keep all of the denominator the same, since that's what I've already done. And I now have, for a magnitude, I have 1/2 scaling the magnitude of 3 plus j. Well, that's now just the square root of 9 plus 1, where that 9 was actually 3 squared. That's now the square root of 10. And what's my angle? My angle now, I have an angle of an inverse tangent of vertical 1 over a horizontal length of 3. Or I now have 1/2 square root of 10 at an angle of about 18.4 degrees. So that now this becomes 18.4 degrees minus 180 degrees for the angle of this new g bar, and that ends up being minus 161.4, and that now with that 0, this g bar of z at z equal to 1/2 plus j 1/2 is not on the root locus. Hopefully now you're starting to remember how to calculate these angles associated with collections of zero factors and pole factors. We want to determine what do those angles look like, and do we have a way of figuring out when those angles might actually sum up to minus 180 degrees and belong on the root locus.